the Flying Wing, the product of years of engineering research by Northrop Aircraft and the United States Air Force. Today, it is the latest answer to aviation's demand for more speed, more range, and greater efficiency of operation. The Flying Wing can carry a larger load faster, farther, and with greater economy than conventional airplanes of similar size and power. Since the Wright brothers airplane first flew it, Americans of this century have seen great advances in air transportation. Few men indeed can see the Flying Wing in operation without saying, the plane of tomorrow is flying today. That mechanical wings could carry him into the sky, airmen have dreamed of the ideal airplane, one of maximum efficiency, in which every exposed surface would have the greatest possible useful purpose, contributing to the lift of the flying machine. 24 years of research and millions of hours of work are behind the production of these new aerial giants. The designer, the engineers, and many other men working with Northrop Aircraft have long had this dream and have turned it into a reality, the Flying Wing.
This aeroplane was developed as an effective way to solve the old problem of reducing drag. Drag's rather hard to describe. A simple definition is to say that it's the resistance of the air to an aeroplane's forward passage. You've felt drag by putting your hand out of a car window, and probably you've noticed that you can reduce it by turning your hand edgewise, presenting less surface to the wind. In the Flying Wing, we've reduced drag by designing an airplane with a more efficient form. Its shape creates less resistance to forward motion and passes through the air more easily. Here, I'll illustrate it for you. Primitive man used a sled to transport loads greater than he could carry. This sled rubbed on the ground, just as aeroplanes rub against the air. It took sheer power to overcome the friction or drag of this conveyance. The larger the sled, the more drag surface it presented, and consequently the more power was required to overcome this drag. The logical solution lay in reducing drag to a minimum. So man developed the wheel, which permitted transportation of equal loads with greatly reduced power, or increased the loads and speed with the same amount of power. Since the beginning, aviation design has been confronted with much the same problem as was primitive man. Today's basic aircraft design still has unnecessarily large drag forces. The engines, cowlings, and the nacelles, the tail surfaces used for stability and control, the bulky extended fuselage. They all are causes of drag. Drag to be overcome at the expense of speed, operational range, payload, and power. In the Flying Wing, we have reduced drag by removing the external engines, cowlings, and the nacelles, the tail surfaces, and finally the fuselage itself. Now we sweep back the wings for purposes of balance, control, and stability. And we see a picture of the basic Flying Wing. And that briefly is what has been done about the problem of drag. Rather than try to overpower it, we've reduced it, knowing that when we eliminate the cause, we eliminate the effect. We now have an airplane which, due to its increased efficiency, is capable of transporting a given load 25% farther or faster than is possible with an ordinary airplane using the same power. That is what is meant by efficiency of design. Our second objective was greater efficiency of structure. In order to illustrate efficiency of structure, We can use these charts for comparison. Here is a massive bridge structure. Massive because of the engineering principles. Notice that all loads are transferred to central, concentrated points. This requires a ponderous, expensive structure to sustain the loads and resist the applied stresses. Stresses that are multiplied in turn by leverages of the spans. Now here on the same highway, carrying the same traffic load, is an economical causeway type of bridge. It does the same job as the first bridge, with a much simpler structure and a fraction of the material. The answer is simple. Stresses are absorbed and weights are sustained by the individual units or pilings. And in the same way, this comparison may be applied to conventional and all-wing aircraft. In the ordinary type, the lift which carries the load works on the wing from tip to tip, but the bulk of the weight is centrally located, necessitating heavier wing construction, particularly at the roots or points of suspension. In the flying wing, the same weights, distributed over the span of the wing, are sustained by individual areas or lift forces, permitting a large saving in structural weight at no sacrifice of strength. This saving is convertible to additional payload or fuel. And that, very simply, is what is meant by efficiency of structure.
Today, Northrop men know well that by combining efficiency of design and efficiency of structure, the result is a high-lift, low-drag flying wing, which can carry a greater load, carry it farther, carry it higher, and carry it faster than conventional airplanes of similar size and power. At far-flung bases and remote corners of the globe, large hangars to house big airplanes are usually hard to find. When these planes are repaired and maintained, the men must work in the open, often in bitter weather, which slows them down and makes the task far more difficult and costly in time and money. But not the flying wing. To shelter the wing requires only a small and modest structure, hardly more than a large Quonset. Placed on dollies, the wing can be trundled sideways into its hangar, a hangar that is small, economical, and easily constructed. As easy to maintain as it is to house, the flying wing is built low to the ground and can be easily serviced. Short ladders or low platforms available at any airport are all that are required to reach almost any part of even a large flying wing. Where outdoor storage is necessary, especially during cold weather, this is a great aid when all surfaces must be cleared of ice or snow prior to takeoff. With these additional advantages, it is little wonder that forward-thinking aviation experts already are envisioning the day when giant flying wing transports will enable world air travelers to fly faster and farther at reduced fares in a degree of comfort surpassing the most modern ocean liner.
Tailless folly, I calls it.
Well, sounds as if someone has an opinion on the flying wing.
Now I ask you, who ever heard of airplanes without tails? Birds have tails, haven't they? If they didn't need them, they wouldn't have them. Flying wings.
Now there's a real expert, an authority on any subject. His ancestors were all authorities too. For instance,
Steamboats. Bah. It's ridiculous. Who ever heard of a boat without sails? Fulton's folly, I calls it. Steam trains. Ah, it's ridiculous. Who ever heard of cars without horses? 18 miles an hour, they say. Flying machines. Ah, it's ridiculous. Who ever heard of a man flying? Never be practical.
Who ever heard of an airplane without a tail? No stability, I tell you. Won't be able to fly. They'll never get that thing off the ground. They should have asked me. I've studied a little bit about airplanes.
of that group of skeptics who just can't understand any scientific advancement and won't believe it when he sees it. An open mind and a little inquiry would disclose the fact that the engineers haven't changed basic principles of stability at all in building the wing. They've merely arranged the control surfaces in a different manner, in a form our skeptic doesn't recognize, thereby reducing drag by eliminating the tail surfaces and the fuselage that supports them. Yes, it's just about that simple and logical. Remember as a youngster when you seesawed on a plank? Sometimes there was a heavier boy on the other end and you had to move out further to establish a balance. With both of you at the ends, your little brother had quite a time moving the plank. But once in balance, you could both move in and out proportionately to maintain that balance. And when you were close to the pivot, little brother could swing you lots easier than when you were out at the end. Now the airplane is balanced about its center of gravity in the same way as the seesaw was on its pivot. And when all of its weight is concentrated close to the center of gravity, as it is in the flying wing, the size of the tail can be reduced or moved much closer to the wing, and the same degree of stability and control will be retained. Here is a top view of an ordinary airplane, and this is what the skeptic failed to investigate. If the load usually spread out the length of a fuselage is carried in the wing close to the center of gravity, then the fuselage can be removed and the tail moved up close to the wing. Now, the tail has much less work to do and therefore requires a shorter moment arm. Swept back or V-shaped wings are coming into general use even on conventional planes because of their recognized advantages in the reduction of drag at high speed. Thus, the wing is simply swept back, and one half the tail is combined with each wingtip. All the original elements needed for stability remain completely effective, but over half the drag of the original airplane has been eliminated. Having already discussed efficiency of design, structure, and maintenance, there's but one final point: operation. Extremely important in any aircraft is efficiency of operation. The handling characteristics of the wing are important to the pilot.
That's right. Makes a lot of difference if a man who flies a plane likes the way it operates. Because of its stability, ease of handling, and maneuverability, the wing is as simple to fly as a conventional type airplane. Despite its 100-ton gross weight, it still responds to fingertip control pressures. But let's get aboard and I'll show you the inside story. First, the controls. The flight controls in the cockpit operate in a normal fashion and differ very little from those in a conventional plane. Foot pedals operate the rudders, which consist of double split flaps, similar to dive flaps, located at the wingtips. When a rudder pedal is depressed, the flaps open to produce drag at the required wingtip. Here's an easy way to explain the action of wingtip rudders. Notice that when drag or pressure is applied to a wingtip, the plane pivots around its central axis, exactly as if rudder were applied. Consequently, our wingtip rudders give us the same control as the rudder on a standard type plane. On the flying wing, both pedals may be operated at the same time. This creates an air brake effect, increasing the rate of descent or reducing the airspeed, a valuable asset in landing a clean modern airplane of this type. This air brake feature is the only variation from a conventional control arrangement. Longitudinal and lateral control are maintained by elevons, a combination of the standard elevators and ailerons. When the control column is pulled back, the elevons, located just inboard of the rudders, are moved upward, causing the wing to climb. Forward movement of the control column moves the elevons downward, resulting in an opposite or diving effect. These operations of the control column and the elevons produce the same effect as the elevators on a conventional type airplane. Lateral rolling effect is achieved by operating the control wheel in the normal fashion. This works the elevons in the same way that ailerons are operated on a standard ship. For example, turning the wheel to the left raises the left elevon and depresses the right, causing the airplane to roll to the left. By turning the wheel to the right, the plane will roll to the right. The plane can either climb and turn or dive and turn by using longitudinal and lateral control at the same time.
Okay, Frank, let's start the engines.
Hello, Tower. This is Air Force 2367. Taxi clearance, please.
With its 8 jet engines, the Wing is one of the most powerful planes in the air. Ground handling and taxiing are identical to that of any other large airplane having a steerable nose wheel. This ease of handling simplifies parking and storage operations. Notice that the pilot of the Flying Wing has excellent forward, downward, and round-the-clock vision, which minimizes taxiing hazard.
Hello, Tower. This is Air Force 2367. Ready for takeoff. Over.
Air Force 2367, this is the tower. Clear for takeoff.
2367. Roger.
In a matter of seconds, this 100-ton giant is airborne. Notice its phenomenal rate of climb. Ease of operation, together with low noise and vibration levels, make long-distance operation almost a pleasure. Because of the pressurized and temperature control, grueling hours of long-range flying can be accomplished with a minimum of pilot fatigue, even at altitudes above 40,000 feet. As pilots know, the Flying Wing is an easy plane to handle. When the rudder pedal is depressed, drag is induced by the opening of the split rudders, and the plane is pulled in that direction. Both rudders are depressed, an air brake effect is created for short approaches or steep descents over landing hazard. Normal control column movement results in a climb, a dive, or a bank is desired. controls operated by dual hydraulic systems, plus an electrical standby, the Flying Wing is the most maneuverable large airplane in the skies. Proved and powerful weapon, a plane that can hold its own against enemy fighters. The wing has a small frontal area and profile, making it difficult to hit or to detect with radar. With its relatively low wing loading and high speed, the wing is capable of defensive or offensive maneuvers that would stall out most fighters, particularly at high altitudes, where the rarefied air places limitations on airplanes with high wing loadings. Imagine you're an attacking puck. Not much to hit in this slim, clean line, is there? Especially if it's going away at more than 500 miles an hour. Should one or more engines be knocked out, the wing is still a formidable fighting machine. It can be effectively maneuvered by making a slight adjustment in trim. Even with all the engines on one side inoperative, it has good performance, flies easily and efficiently. As a bomber, a long-range high-payload cargo carrier, or a giant passenger transport, the sleek, knife-edged Flying Wing has as its keynote efficiency. Efficiency of design, efficiency of structure, efficiency of maintenance, and operation. It is the most useful and efficient airplane the world has yet seen.